Because it's easy to look and say, oh, well, that's, I don't understand, and hi, what do you want?
I was just looking at you.
Cool. I'm currently standing in the remnants of Winter Storm Helena, which dropped about several inches of snow and even a few inches of ice down in the southeastern portions of the United States. When the Winter Storm Helena was being forecast, though, there was a lot of discussion about different forecast models.
You know, you have the GFS that could be 4 or 5 inches, and then Euro saying, maybe 1/10 of an inch of snow.
Yeah, one of the more aggressive computer models is showing that Danville could receive a foot of snow.
But this computer model, south of Atlanta. But compare that, Mark, to the European model, and look where the snow is, north of Atlanta. So you can imagine, you look at these two computer models and you say, which one's right?
That's because the models were all showing different snowfall totals. And when it comes to communicating forecast uncertainty, it becomes quite a challenge because all these different models have their own little quirks, and it's not really discussed that often. But first, what exactly is a forecast model? So all over the US, we have different weather stations that collect data. We also use weather balloons and satellites to collect atmospheric data. And all these numbers are plugged into the equations which make up the numerical models that you see forecasting on the Weather Channel or your local broadcasting station. And they all pretty much predict the weather. Now, these models are nowhere near perfect, and they take a long time to run. And due to that, we can only forecast up to a certain extent, usually about a week, depends on the model. Also, while these equations describe atmospheric processes fairly well, they aren't perfect, and there are some portions of several equations that we can't actually get the numbers for. For example, if an equation requires, let's say, atmospheric friction, since it's actually a small number anyways, like literally like -3 or -4, probably even smaller than that, we pretty much ignore that part of the equation. We do it by hand. But if you run these models with equations that, kind of just say, let's just forget about this number or this concept. I mean, it's fine when you do the equation maybe once or twice, but models run over time. So these equations are done continuously over time, and if you keep adding these equations together, you're going to get a lot of errors over time. And when you have all those errors or that lack of information add up, the models start to not predict correctly. That's why you often hear meteorologists updating the forecast 24 to 48 hours before a system or a storm hits, because that's when the forecast models are the most reliable. In the United States, we mainly use 3, can you tell? My glove's kind of thick, but yeah, 3 models for forecasting, which is the GFS, the NAM, and the ECMWF. Whoa, that's a mouthful, but it's colloquially known as the Euro model. So the GFS is the American-made model, and it's pretty reliable up to about 5-ish, some say maybe 7-ish days, versus the NAM, which is actually more of a mesoscale/regional model, and it works on a higher resolution grid, which means that it takes into account topography, because mountains and valleys and stuff like that in the ocean, they all play a really big component in weather, and the more world models like the GFS can't really take into account those mesoscale or local features. So that's why the NAM is really good in predicting weather right before it happens. However, as those geographical aspects are included, that kind of complicates the equations, and as the NAM model runs further and further out, it has many more errors than, let's say, the GFS. So that's why the GFS is mainly used for long-range forecasting and the NAM for short-term. For example, in Martinsville, Virginia, which is kind of near where I'm from, we received about 9 inches. The NAM near the end said about 7 to 8, which is pretty accurate compared to the GFS, which had basically 3 to 4 to 5. However, the Euro model is often seen as the most accurate, even though it itself has its own little quirks, and it has outpredicted the GFS in major storm systems such as Winter Storm Helena that hit last January 2015. It caused New York City subway to close for the first time in over 100 years, caused a bit of ruckus because they only got 2 inches instead of 2 feet. Anyways, each of the 3 models are based on slightly different equations, which causes them to have their own little quirks, or what we meteorologists like to call biases. And it's really good to have meteorologists to look at these models because we know the biases and we can kind of correct for it in our forecasts. I hope this video helps you understand forecast models a little better and how we have to take them with a grain of salt, or in the case of this, a clump of snow. I know that was really corny, I'm sorry. But I'm Jessica, and thank you for visiting the Weather Hub.